A very good morning and welcome to my course Basic Electronics Engineering. This course is generally made for undergraduate level BTech degree students of second year. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Baraipur, a college under JIS Group Educational Initiatives. Students, you can personally meet me at college premises, ground floor, physics lab. Or you can also send me your doubts and your query by mail that is given here, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@jisgroup.org. I have a YouTube channel. The link is given here. You can follow my Facebook, my YouTube page. I have also in the Facebook page to provide you the following links of the YouTube page. So already lots of video is uploaded as per markout syllabus. If you want, you can go through that videos, and for any type of doubts and query, feel free to contact me. Now, the following course pages are www.markoutexam.net and www.markoutwb.ac.in. The syllabus is already uploaded in the university website. If you want, you can download the syllabus from there. Now the title of the course is Basic Electronics Engineering. The subject code is ES-ECE 301. It is under the category of Engineering Science course. It has a credit 3 lecture per week. So this course is generally made for BTech degree students of second year, third semester. Apart from all other departments, only the students of mechanical engineering departments have to study this subject as a part of their curriculum for second year, third semester. So, for this subject, I am your subject teacher. Now, today the topic that I will going to be discuss is basics of OPAMP based voltage to current converter and current to voltage converter, and also OPAMP based comparator circuit. So these all topics are under module 2, that is operational amplifier and its applications. Prerequisite for these topics are elementary idea of semiconductor physics. The course objective is to provide an overview of basics of OPAMP based voltage to current converter and current to voltage converter and OPAMP based comparator circuit. So after completion of this topic, student will able to understand the basic principles of OPAMP based voltage to current converter and current to voltage converter, and also the OPAMP based comparator circuits. So in today's class, I am going to discuss the details about converter. One is voltage to current converter, another one is current to voltage converter. Now before going starts with today's class topic, I like to remind you that I have already discussed the details of OPAMP, its arithmetic applications, and inverting and non-inverting amplifier. So when you are going to study that OPAMP as a converter or as a comparator, before that you have to clear your idea about the basics of OPAMP, about the inverting and non-inverting amplifier. These two are the basic circuits, because from there the virtual ground concept that is very much necessary, because when you put the non-inverting terminal at the ground, at the same time for a virtual short concept, your corresponding inverting point is also have a voltage 0 at the same point. So if you apply a voltage V1 at the inverting terminal, ultimately 0 minus V1 is applied to the inverting terminal. So when you are calculating the current, so your current will be 0 minus V1 by R if there is some resistance in the inverting terminal. So these are the basic that you need to know before start with today's class. I have already completed 3 or 4 video lecture classes on that operational amplifier, or in short OPAMP. So students, please go through that videos, and if you feel any doubt, you can contact me. So now in today's class, I will show you and discuss the details about, firstly, the converter circuit, voltage to current converter, and also current to voltage converter, and secondly the comparator circuit based on OPAMP. So hope you will understand and enjoy today's class. So, converter of electrical quantities. Voltage and current are the basic electrical quantities. They can be converted into one another depending on the requirement. So voltage to current converter and current to voltage converter are the two circuits that help in such conversion. These are also linear applications of an OPAMP. So in this chapter, I'll discuss in details. Firstly, the voltage to current converter. A voltage to current converter or V to I converter is an electronic circuit that takes current as the input and produces voltage at the output. So in this section discusses about OPAMP based voltage to current converter. Now an OPAMP based voltage to current converter produces an output current when a voltage is applied to its non-inverting terminal. The circuit diagram of an OPAMP based voltage to current converter is shown here. So in the above circuit, the input voltage Vi is applied at the non-inverting input terminal of the OPAMP. So here it is clearly visible to you. This is the input voltage that is applied in the non-inverting terminal, and here the inverting terminal is grounded through R1. There is a feedback resistance RF. Now, as per virtual short concept, as the voltage, input voltage, is Vi here in non-inverting terminal. So in inverting terminal, this part is also having voltage Vi as per virtual short concept. So this is the basic circuit diagram of an voltage to current converter. Now the voltage at the inverting input terminal of an OPAMP will be equals to the voltage at its non-inverting input terminal. So the voltage at the inverting input terminal of the OPAMP will be Vi. Now the nodal equation at the inverting input terminal, the node is Vi by R1 minus I0 is equals to 0. So from there we can write I0 equals to Vi by R1. Thus the output current I0 of a voltage to current converter is the ratio of its input voltage Vi and resistance R1. So we can write I0 by Vi equals to 1 by R1. So we can write this above equation. The above equation represents the ratio of output current I0 and the input voltage Vi, and it is equals to the reciprocal of resistance R1, the ratio of the output current I0 and the input voltage Vi is called transconductance. We know that the ratio of the output and the input of a circuit is called a gain. So the gain of an voltage to current converter is the transconductance, and it is equal to the reciprocal of resistance R1. Next one, that is current to voltage converter. A current to voltage converter or I to V converter is an electronic circuit that takes current as the input and produces voltage at the output. In this section, discuss about the OPAMP based current to voltage converter. An OPAMP based current to voltage converter produces an output voltage when current is applied to its inverting terminal. Here the circuit diagram is shown below. So you can see here the non-inverting terminal is grounded, and at the inverting terminal we have applied a current, and feedback resistance RF is always there. So as per virtual ground concept, if this point is grounded 0, that means this point should be 0. Now, in the circuit above, you can see the non-inverting input terminal of the op-amp is connected to ground. That means 0 volt is applied to the non-inverting input terminal. So, according to virtual ground concept, the voltage at the inverting input terminal of the op-amp will be equal to the voltage at the non-inverting input terminal. So the voltage at the inverting input terminal of an op-amp will be 0 volt. So from nodal equation we can write minus I input plus 0 minus V naught by RF equals to 0. So from there, rearranging, we can write V naught equals to minus of RT and into I. Thus, the output voltage V naught of the current to voltage converter is the negative product of the feedback resistance RF and the input current II. Observe that the output voltage V naught is having a negative sign, which indicates that there exists a 180 degree phase difference between the input current and the output voltage. So we can write V naught by I is equals to minus of RF. So in this RF equation represents the ratio of output voltage V naught and the input current II, and it's equals to the negative of the feedback resistance RF. The ratio of the output voltage V naught and the input current II is called trans resistance. We know the ratio of output and input of the circuit is called as gain. So the gain of a current to voltage converter is its trans resistance and is equals to the negative feedback of resistance RF. Now the next one, that is comparator. A comparator is an electronic circuit which actually compares the two input that are applied to it and produces an output. The output value of the comparator indicates which of the input is greater or lesser. Now, the comparator falls under the nonlinear applications of ICs. An OPAMP consists of two input terminals, and hence an OPAMP based comparator compares the two inputs that are applied to it and produces the result of the comparison at the output. So in this chapter I will discuss about the OPAMP based comparator. So here there are two types of comparator. One is inverting, another one is non-inverting. So first one, the inverting comparator. Inverting comparator. An inverting comparator is an OPAMP based comparator for which a reference voltage is applied to its non-inverting terminal and the input voltage is applied to its inverting terminal. The comparator is called as inverting comparator because the input voltage which has to compare is applied to the inverting terminal of the OPAMP. So now I will show you the circuit diagram. So this is the circuit diagram. It is clearly visible that this is the input voltage at the inverting terminal, and this is the reference voltage as applied in the non-inverting terminal, and here you will get the output. The operation of an inverting comparator is very simple. It produces one of the two values, plus V set and minus V set, at the output base on the values of its input voltage Vi and the reference voltage V reference. The output value of an inverting comparator will be minus V saturation, for which the input Vi voltage is greater than the reference voltage. Now the output value of an inverting comparator will be plus V saturation, for which the input Vi is less than the reference voltage. Now an example, let us draw the output waveform of an inverting comparator when a sinusoidal input signal and a reference voltage of 0 volt are applied to its inverting and non-inverting terminal respectively. So this is the figure. The operation of this circuit is during the positive half cycle of the sinusoidal input signal, the voltage present at the inverting terminal of OPAMP is greater than 0 volt. Hence the output value of the inverting comparator will be equals to minus V saturation during positive half cycle of the input signal. Similarly, during the negative half cycle of the OPAMP, of the input signal of the OPAMP, the voltage present at the inverting terminal of the OPAMP is less than 0. Now, hence the output value of the inverting comparator will be equals to plus V saturation during negative half cycle of the sinusoidal input signal. Now I will show you the following figures, also the input and output waveform of the inverting comparator when the reference voltage is 0 volt. So you can see the corresponding input and output. So input is a sinusoidal wave and output is a square wave. In this figure, we observe that minus V saturation and plus V saturation are from plus V saturation to minus V saturation, the output is varying. Whenever the sinusoidal input signal is crossing 0 volt, in the other word, the output changes its value when the input is crossing 0 volt. Hence, the above circuit is also called an inverting zero crossing detector. Non-inverting comparator. Now, an non-inverting comparator is an OPAMP-based comparator for which a reference voltage is applied to its inverting terminal and the input voltage is applied to the non-inverting terminal. This OPAMP-based comparator is called non-inverting comparator because the input voltage, which has to be compared, is applied to the non-inverting terminal of the OPAMP. So here the operations of a non-inverting comparator is very simple. It produces one of the two values, plus V saturation or minus V saturation, at the output based on the values of input voltage Vi and the reference voltage plus V references. Now the output values of a non-inverting comparator will be V saturation, for which the input voltage Vi is greater than the reference voltage V reference, and the output values of a non-inverting comparator will be minus V saturation, for which the input values Vi is less than the reference voltage. Now let us draw output waveform of a non-inverting comparator when a sinusoidal input signal and reference voltage of 0 volt are applied to the non-inverting and inverting terminals of OPAMP respectively. So the operation of non-inverting comparator is like: during the positive half cycle of the sinusoidal input signal, the voltage present at the non-inverting terminal of the OPAMP is greater than 0 volt. Hence, the output value of a non-inverting comparator will be equals to V saturation during the positive half cycle of the sinusoidal input signal. Similarly, during the negative half cycle of the sinusoidal input signal, the voltage present at the non-inverting terminal of an OPAMP is less than 0 volt. Hence, the output voltage of non-inverting comparator will be equals to minus V saturation during the negative half cycle of sinusoidal input signal. Now, this is the diagram corresponding input and output shown in figure. Now, from the above figure, we can observe that the output transition either plus V saturation to minus V saturation or minus V saturation to plus V saturation. Whenever the sinusoidal input signal crosses 0 volt, that means the output changes its value when the input is crossing 0 volt. Hence, the above circuit is also called a non-inverting zero crossing detector. Now, these are the reference book that you can refer. The evaluation process are same. Students have to appear for a 70 marks end semester exam and 30 marks internal exam, out of which 15 for exam, 10 for assignment and 5 for attendance. Hope all of you have enjoyed and understand through this class. In next class, I will discuss about logarithmic and anti-logarithmic amplifier and rectifier. So, thank you.